Hi, this series of video lectures is meant to cover some of the mathematical prerequisites for doing quantum mechanics. This time we are going to study quantum mechanics in physics, and the mathematical language in which the laws of quantum mechanics are written is linear algebra. So we need to make sure that we understand and we know how to solve problems in linear algebra very well. You have already covered linear algebra to a reasonable extent in your Mathematical Methods 1 course. So I don't have to teach you linear algebra from scratch. Instead, what this lecture series will do is it will give you a review or a recap of things that you already know and you're already familiar with. So we will cover all of the essentials and we will look at some examples. At some points, you might find that what we are doing over here is a slight generalization of the linear algebra that we studied in Math Methods 1. For example, over there you probably only looked at vector spaces over the field of real numbers. Over here we will generalize it to the field of complex numbers. So you will find a few generalizations here and there. By and large, the concepts will be the same. Towards the end, maybe a few new concepts which you have not seen before will be discussed. If at any point you find that there is a certain topic over here which I'm assuming has been covered in math methods, and so I'm running over it and not spending much time on it, feel free to catch me during class and ask me about it, and then we can have a detailed discussion or maybe even a separate lecture on that if the need arises. Okay. The discussion that I'm doing over here in these video lectures is largely taken from the book by Shankar, Principles of Quantum Mechanics. It's a very good book for quantum mechanics in general, and chapter 1 of this book deals with all the linear algebra, the mathematical prerequisites that you will need for doing quantum mechanics. So the topics of linear algebra that I will be discussing, also the ordering and the logic in which I will be going through them, is based on Shankar chapter 1. So if you're the kind of person who prefers to just to not listen to lectures and instead pick up a book and start going through it and solving problems from it by yourself, feel free to do that. You can look at chapter 1 of this book. Again, I'm not going through all the topics that Shankar discusses because it's a pretty detailed chapter, and some of the things might not be required for our level, for a first undergraduate level course in quantum mechanics. So it's not all the topics from that chapter that I'm covering. I'm skipping some things which I feel might not be that relevant for us right now. But otherwise, that book is great. As with all physics and maths courses, just listening to these lectures will not be enough. You will need to solve a lot of problems in order to make sure that you know what you're doing in linear algebra. Shankar's book gives a few examples and exercises that you can work through. Apart from that, you can also look at Shom's outline, and I think the book is called Linear Algebra, which also has a lot of problems, both solved and unsolved. So that's a very good resource for you to see how problems are solved and then pick up problems and then solve them yourselves. Okay, so that's it as far as introduction is concerned. Let's jump right into it. So linear algebra deals with objects called vectors. Now vectors you're familiar with from your high school days. You have seen various vectors in physics: displacement vector, velocity vector, acceleration vector, force vector, electric field, magnetic field, angular momentum. These are all vectors as you know them. And the way they were introduced to you back then was by saying that a vector is something that has magnitude and direction. So for example, velocity has a magnitude, of course, the speed, but it also has a direction. So you can decompose it into various components and you can look at it component wise. What we are doing over here in linear algebra is we are going to generalize this concept of a vector. So we no longer think of it as simply as an object that has magnitude and direction, but we come up with a bunch of properties that will be useful to us. So we define a vector in terms of certain properties that they have, that they need to satisfy in order to be called a vector. And the collection of all of these vectors is called a vector space. So vectors belong to a vector space. And you can say that linear algebra is the study of vector spaces. Now, yes, the old image that you have of vectors in terms of some quantity and then you put an arrow on top of it, it's a nice intuitive way of understanding what is going on. So whenever we are discussing vectors in linear algebra, we will be doing it in a very general abstract sense, but it's a very good idea to, at the back of your mind, keep relating those abstract concepts with what you already know in terms of these velocity, acceleration, displacement vectors. So for example, when you're talking about addition of vectors or multiplying by a scalar quantity, you always at the back of your mind think of it in terms of what you know about your vectors in three-dimensional space. Okay, so let's start formally by defining what is a vector space. So we are doing a definition. A vector space, and let's call it capital V, is a collection of objects called vectors, and I'm going to denote them with this very strange kind of notation which you've probably never seen before. I'll call them V, W, and so on. These are all vectors. So the name of the vector is V or W, but I'm putting them inside this strange kind of an object, and this is called a ket. Why is it called a ket? Well, later I'm going to introduce also something pointing the other way, and this is going to be called a bra. And the idea is when you put them together, it becomes a bracket. Like that's the way the name was formulated by Dirac. So we are calling these kets as vectors, and they need to satisfy certain properties. So for example, what are these properties? If V and W are vectors in this vector space, you know this notation, right? Belongs to the set. So if V and W are vectors belonging to this vector space, then their sum must also belong to the vector space. Second thing, if V is a vector in the vector space, then even if I multiply this by some scalar quantity, this also belongs to the vector space. So A is a scalar. You can think of a scalar as just being a number. And well, no, I'll come to fields in a little bit. And then you can combine these and you can say that if V and W are vectors in the vector space, then I can multiply each of them by some scalar quantity, and this sum, A times vector V plus B times vector W, must also belong to the vector space. So A and B are both scalars. So there's a special name for doing this kind of thing. We call this a linear combination of vectors V and W. Why linear? Because we are not doing any V square or W square. It's just simply adding them up. We've not defined any notion of multiplying vectors yet. So this is called a linear combination or a linear sum of these vectors v and w. Okay. If I first add up two scalars and then multiply it by a vector, then this is just a times v plus b times v. So the scalar multiplication is distributive. So once again, I'm reminding you, I'm showing you all of these properties. Always think of it in terms of your original arrow vectors. So for example, property 1 says that if you add two vectors, then the sum of those two is also going to be a vector. If you take a vector and you multiply it by a scalar quantity, remember that's just stretching the vector. So it's still a vector. Similarly, you can scale and add two vectors, you still get a vector in the end, and so on. So always keep in mind what you know about vectors from high school. We know that vector addition is commutative. Doesn't matter what order you add them in. V plus W is the same as W plus V. It is associative, meaning V plus W plus X is the same as V plus W plus X. So whether you multiply the second and the third first, or you multiply the first and the second first, it is going to be the same. Now here come two very important properties, and let's put them on the next page. In any vector space, there exists a null vector. And let's null, and we will denote it by 0. And the property of this null vector is it acts like the 0 vector. So you add any vector to it, you get back that same vector. Null vector 0 such that any vector v when you add to 0 gives you back v. And then also for every vector you have what is called the additive inverse, means the negative of that vector. For every vector v, there exists its additive inverse, and this is denoted by minus v, such that when you add a vector along with its additive inverse, you get the null vector. So actually these properties are, I'm going to mark out some of them which are the crucial ones. These two, which is that the sum of two vectors is a vector, and vector multiplied by a scalar quantity is also a vector. And these two, existence of the null vector and existence of an additive inverse for any vector. You can think of these four as being the most fundamental ones that define a vector space, that define the properties of a vector. So again, think of these in terms of the vectors in 3D. So you're used to seeing vectors in 3 dimensions, or what we call R3, so 3 real axes, and over there you're used to seeing some vectors which might look like 3i plus 2j minus 5k, something like that. And then vector addition, scalar multiplication, existence of the 0 vector, which is just 0i plus 0j plus 0k. And of course you know that for every vector v, there is also a negative vector minus v, which in this case would be minus 3i minus 2j plus 5k, such that when you add v and minus v, you end up getting 0, the 0 vector. Now these numbers over here, 3, 2, minus 5, these are all called components of a vector. So over here, these components are real numbers. In general, you can also have a vector which has complex components. And what are these components? They are actually just scalar quantities. And they belong to a set called the field. And same with the scalars that I have multiplied these vectors with over here in properties 3, 4 and 2. These, when I say scalars, what I mean is they are just some numbers and they belong to what is called a field. So over here, this vector v that I have written over here, v is a vector and it belongs to this R3, is a vector defined over the field of real numbers. But I could also have some other vector w, let me call it, and let's say this is 1 plus 2i, I being square root of minus 1, I hat plus 5 minus 4i j hat, something like this. And now this is a vector defined over the field of complex numbers. So field is nothing but the set of numbers from which you are taking the components of your vector. That is all that it is. So, and in our cases of interest, we are only going to be talking about the real field or the complex field. So real field is referred to as R, complex field is referred to as C. But for all essential purposes, it's just the numbers that we are dealing with. Okay, so now let's take some examples of vector spaces. So first example I will take R2. R2 is basically just numbers of the form x comma y. And I will define the operation of addition as just component wise addition. So you add the x component, the first number, and you add the y component to the second number. Is this a vector space? Let's see. Let's check if those four properties are satisfied or not. So if you take x1, y1, and if you, so this is one vector, let's call it v. And if I take another vector, let's call it x2, y2. And if I add them up, what I get is x1 plus x2 and y1 plus y2. Is this also in R2? Yes, this is also in R2 because it has one real number over here, comma, one more real number over here. Okay. If I multiply one of them by a scalar, so if I define a v, this is going to be a x1, a y1. Oops. Is this also in the set of R2? Yes, this is also in R2 because one real number, one real number. Is there a zero element in this in R2? Yes, there is. There is an element which is just 0, 0, which if I add to any vector, I will get back that vector. Is there an additive inverse? Yes, there is. For any v, I can find a minus v and this is just given by minus x1 comma minus y1. So additive inverse also exists. So we conclude that R2 is a vector space. And you can think of this object x comma y as just, or yeah, this v x comma y as just being x1 I hat plus y1 j hat. So you're used to seeing vectors in terms of these I hat j hat vectors, but you could just as well have represented this just as this ordered pair x1 comma y1. It's the same thing. Everything works out. Your addition is component wise, scalar multiplication happens with each component, and so on and so forth. So R2 is a vector space. So R2, yes, it is a vector space. What if we take R3? So now this is a set of three real numbers x, y, z. I want you to verify for yourself and convince yourself that this is also a vector space for the exact same reasons. Everything that we said for R2, in which there were only two components, is also going to work over here for R3, which has three components. Let's take one more example. All the points on the line y equals mx. So graphically, if I were to write it, draw it, it's basically all of these lines, all of these points. So x and y such that y and x are related by this formula, y equals mx. Do all of these points form a vector space? Let's see. If so, each vector I can write it as, let's say, some x1 comma y1, but y1 is just mx1. That is the definition of this line. So every point on this I can write it as x1 and mx1. It's not very clear. Okay, so let's see. If I take two vectors like this, x1 mx1, and I'll take one more which is x2 mx2, will there sum lie on this line again? Yes, it will, because if I take the sum, I will get x1 plus x2 and m times x1 plus x2. So this is also of the form something and m times something. So that also lies on that same line. You can also think of it just diagrammatically, just imagine in your head, if you take two vectors, both of them pointing along that same y equal to mx line, you add two of them, you will still be along the same line only. So the sum of the two vectors is also a vector in this space. Similarly, if I do scalar multiplication, you take a vector and scalar multiplication is just stretching, so it will stay in the same direction. So scalar multiplication also gives you a vector in this vector space. Is there a zero element in this vector space? Yes, there is. That is again this point 0, 0. And similarly, for any vector, there is also the negative of that vector, which also lies on the same line. Therefore, all points of this kind, y equals mx, are so this is a vector space. The line y equal to mx, or all the points on this line y equal to mx, represent a vector space. So whether it's y equal to x, y equal to 2x, anything, any of them is a vector space. What about all points on the line y equals mx plus c, where c is not 0? Let's draw this diagram now. So this is going to look something like this, let's say. Now question is, if I take two vectors along this line or 2 points along this line, and if I add them up, will I still get a point along this line? Turns out there is no guarantee. But it's much easier to see why this is not a vector space, simply because this 0, 0 is not on this line. There is no point on this line which can act as the zero vector or the null vector. Therefore, this is not a vector space. Okay. Let's take a slightly more complicated example. All 2 cross 2 matrices. Do these form a vector space? So this vector V is some A1, B1, C1, D1. So this is a 2 cross 2 matrix. I'm calling this a vector, and I want to check whether this set of all 2 cross 2 matrices is a vector space. So let's check. I'll take one more vector like this, A2, B2, C2, D2. If you add the two, do you still get a 2 cross 2 matrix? Yes, you do. If you multiply one of them with a scalar quantity, so if I do k times V, I'll get k times A1, k times B1, k times C1, k times D1. This is still a 2 cross 2 matrix. So yes, scalar multiplication also works. Is there a zero element, a null vector? Yes. This 0, 0, 0, 0 matrix. If you add it to any other matrix, you will recover that matrix. So this is a null vector. Is there an additive inverse? Yes, there is. If I just take minus A1, minus B1, minus C1, minus D1, then that is the additive inverse of the vector V. So all 2 cross 2 matrices form a vector space. What if I take all 2 cross 2 matrices of the form 1 B1 C1 D1? So again, these are all 2 cross 2 matrices, but with the requirement that the 1, 1 element has to be 1. So let's see. Let's take a vector V, which is 1 B1 C1 D1, and I'll take a vector W and I'll call it 1 B2 C2 D2. When I add them up, V plus W, I get 2 B1 plus B2 C1 plus C2 D1 plus D2. So the 1, 1. So just to recap, if you add two vectors, two matrices of this form, then over here in the 1, 1 element, you will end up getting a 2. It's not a 1 anymore. So it doesn't belong to the vector space, because that vector space is defined as all matrices which have 1 sitting in that corner. Therefore, no, this is not a vector space. What if I take all 2 by 3 matrices of the form 0 x y 2x minus y z? So all 2 by 3 matrices that can be written in this form. You can check that if I add any two of them, it will be of the form 0 x1 y1 2x1 minus y1 z1 and 0 x2 y2 2x2 minus y2 z2. And when you add them up, you will still get something of the form 0 x1 plus x2 y1 plus y2 2 times x1 plus x2 minus times y1 plus y2 and z1 plus z2. So this also has the same form. Similarly, you can check with scalar multiplication, you can check existence of zero, existence of additive inverse, all of them will work. So this is also a vector space. Okay, so these are some common examples of what of vector spaces.